Hello, welcome back to the next part of the session. In the last session, we discussed how modern microcontrollers offer multiple functions on any given pin, and this allows us to fit more functions within the limited number of pins available on a microcontroller, and it becomes the responsibility of the programmer, that is the system designer, to ensure that writing an appropriate program to select whatever functions they need for a given application are appropriately selected. Now, it may also happen that you need two functions, and unfortunately on a given microcontroller both those functions are mapped to the same pin, right. I can take an example. Let us look at this diagram here, and imagine that you do want to use pin number 23 because it offers you ADC channel 0. It also offers you interrupt on this pin called PC int 18, PC int 8, and you want both these functions at the same time. Now, the way they are mapped on a single pin, it will not be possible, and therefore you may either have to compromise by finding some other pin which has similar functionality, or if you were to use more recent, more advanced microcontrollers, you would find that in such microcontrollers a given function may be available not only on one pin, it may be available on multiple pins, and so you can judiciously use a function on a different pin so that you can continue to use the other function on that pin that you wanted to use. And so this is this point, and I will illustrate it by looking at the data sheet of such a microcontroller. This is the data sheet that I have for you to illustrate this point of how how functions could be available on multiple pins. Here, if you look at this pin, this function, this is I square C module, and this is the clock for the I square C module. It is available on two pins, pin number 34 and pin number 74 also. Now, if this pin happens to, if on pin 34 happens to have another function, you can forego that function and instead use pin number 34 to provide I square C clock, which in the earlier case where a given pin would have 2 or 3 functions, and if those functions were not available on other pins, you would be stuck. And so this is an important point which you may consider while selecting an appropriate microcontroller. Then you need a microcontroller to store your program. So what is the kind of memory is available? So it turns out that program memory of in the range of 1 kilobyte to a few megabytes are available on contemporary microcontrollers. Obviously, you will choose a microcontroller with less amount of memory when your application is small. It would also reduce the cost of your application, cost of the microcontroller, and in case you need more memory, you would choose an appropriately large amount of memory on a microcontroller that you want to consider. There is another feature that these have, and this is called, what is the meaning of lock? Now, let me illustrate this point, especially in the context of the three methods of implementing a given application, 3 methods of implementing the embedded computer. And you would recall that the first method was the general purpose approach. The second was the application specific. Processor. General purpose processor approach. Now, in the case of general purpose processor, you would have the microprocessor here, and you would connect it to a ROM of appropriate variety, maybe a E square PROM, and you would have RAM. Now this ROM device consists your program, which is the intellectual property of your product, right? Now a competitor may find it very convenient to buy your product, remove this ROM from the circuit, put it into a device that is commonly called EEPROM programmers. They are also capable of reading the contents of EEPROM, and they can replicate your system by copying the contents of your program. So if your product is implemented using the general purpose processor approach, it has the potential of being duplicated very easily. And therefore, a better method is to use this microcontrollers with integrated program memories, especially which have a lock function. You can invoke this lock once your program development is complete. You can secure the contents of these memories by selecting the lock feature, and thereafter nobody would be able to read the contents of this memory by connecting it to the programming pins. And this is a very important feature to consider, especially when you are making a product. Then these microcontrollers have SRAM, which is used as data memory, and the value of these, the amount of SRAM available on these microcontrollers ranges from anywhere from 0 kilobytes, that means no memory at all, to tens of kilobytes. Now there is a important question that comes to our mind, that if the amount of memory available on a microcontroller data memory, that is SRAM on a microcontroller, is 0, that is no memory, how are we going to store our variables? One, because the data memory is used for several purposes. One, for storing variables. Two, for passing parameters from the main program to the subroutine, and very importantly to store return address what is commonly called as a stack. On the stack you would store the return address of the program from which you would call a subroutine. So before going on to the subroutine, you would store that address to which you have to come back after the subroutine has been executed, and typically you would use data memory to store that. Now the big question in front of us is, if we have selected a microcontroller in which there is no RAM, how are we going to perform these three functions? And the answer is very simple. Typically such microcontrollers which do not offer any RAM would usually be of the RISC category, RISC architecture, and in RISC architecture there is usually large number of internal registers, and therefore you could use these registers for storing your variables, and you could use the same registers for passing the parameter to a subroutine. Of course, if your application is large that you cannot do with the number of registers available, clearly this is not an appropriate microcontroller for this application. You must find a microcontroller which has some or suitable amount of SRAM available. But for very small applications, it is possible that you may get away without using any RAM. It still poses, how do you store the return address? In such cases where the microcontroller does not have any SRAM, instead of using RAM for the purpose of a stack, such microcontroller offer what is called as a hardware stack. What is a hardware stack? Meaning there is a dedicated storage memory specifically for the purpose of storing return addresses. Now because if you have a regular microcontroller with some amount of RAM, the entire RAM could be used for storing return addresses. When does the size of the stack grow? When you call a subroutine from within a subroutine from within a subroutine, what is called as nested subroutines. When you have too many nested subroutines, they would increase the size of the stack. As you return from a subroutine, it would vacate the stack, and therefore the stack size would reduce. In the case of hardware stack, the storage is limited, usually 3 or 5 return addresses, and therefore you cannot have too many nested subroutines in such microcontrollers which do not have RAM, and instead there is a dedicated hardware stack. In such applications, in such microcontrollers, you cannot involve too many, you cannot write too many nested subroutines. So, this is a compromise that you would have to do, and the compromise is so that you can continue to utilize this inexpensive microcontroller for some cheap applications. But this is an important feature to keep in mind, and that is the meaning of SRAM with 0 amounts of memory. So, we have considered the availability of functions on multiple pins. We have considered how much flash memory may be available in various microcontrollers. We have considered how SRAM, the amount of SRAM available. Now, let us come to another point, and that is, apart from flash memory and SRAM, another type of memory is usually available on microcontrollers, and that is the EEPROM. EEPROM stands for electrically erasable programmable read-only memory, and I use a term which I have coined, I call it semi-constants, and the amount of EEPROM available could be anywhere from 0 kilobytes, which means no EEPROM, to a few kilobytes. What is semi-constant? You may not have normally heard this term. I have specifically sort of created it to indicate a constant, a value which is constant most of the time, but once in a while you may want to change it, right. Can I give an example? Most certainly. Imagine that you are a manufacturer of bicycles, and modern bicycles, people like to have a computer on those bicycles which are called bicycle computer. What does a bicycle computer do? Usually it will tell you the distance traveled, the acceleration, the amount of time you took for a given journey, right. Now, how would it measure all these parameters? On the wheel of the bicycle, these are the axle, and these are the spokes, and then from this you have probably the fork which is holding the wheel at the center. On the fork, on the spokes of the bicycle, you attach a small magnet, and on the fork you attach a Hall effect sensor. When the wheel rotates, this magnet passes in the vicinity of the Hall effect sensor, and the Hall effect sensor indicates that by maybe a pulse, and so as the wheel rotates you will keep on getting pulses. The time between two pulses is the time that the bicycle took for one complete rotation of the wheel, and therefore if I know this time, I also know that during this time I have travelled, the bicycle has travelled 2 pi r, where r is the radius of the bicycle. I have travelled this much distance, and so if I know the time and I know the distance, d is equal to 2 pi r, if I divide it by time I get speed, and so on, and from that I can calculate acceleration and so on. Now, if typically a manufacturer of bicycles does not manufacture one size of bicycles, they manufacture several sizes, and these sizes are classified in terms of the wheel radius. And so, would it mean that this manufacturer, if they are making 10 different radius bicycles, that they would have to stock 10 different bicycle computers? That would be very impractical, and it would lead to needless stocking of inventory. What we should have is a mechanism so that the end user, or maybe the dealer, just before making the sale of the bicycle, adjust the radius in the bicycle computer to reflect the radius of the bicycle, and thereafter when the user uses that computer on that particular bicycle, it computes the distance and velocities appropriately. Now the problem is, where should the value of the radius be stored? If the radius is stored on the flash memory, that is the program memory, it cannot be altered. If it is stored in the RAM, then every time this bicycle computer is switched off, it would be lost, and that is where. So, I call this radius, the value of the radius, as a semi constant. Most of the time it remains constant, but once in a while it may change. In the case of this bicycle computer, if this computer is removed from this bicycle and has to be fitted on a bicycle with different radius, then this radius has to be changed, otherwise it would remain constant for the rest of the time that it is used on that bicycle. So, this is a semi constant, and where would you store it? This is where we go back to our slide and say the place we would store it is an E square prom, because E square prom is runtime. You can modify the contents of E square prom at runtime, meaning as the application is running, you can change the value of the value stored in the E square prom. So, in our application, the value of the radius could be stored on an E square prom. Through the menu, the user can select that they want to change the value of the radius. Maybe on their bicycle computer there is a up and down switch, and you can adjust the value reflected on the display to reflect the correct radius of the bicycle, and then you press enter. It will update the value of the radius stored in the E square prom, and thereafter when you use the bicycle computer, it would show the correct, it will use the correct radius to compute the distance and velocity and so on and so forth. So, this is the meaning and function of E square proms on modern microcontrollers. Let us see another, go to the next slide. Now, on modern microcontrollers, you do not have to worry about the limited number of pins with the interrupt capability, because now most of these microcontrollers offer almost all the pins with a feature called interrupt on pin change. And I could show you the diagram of a microcontroller here, the pin diagram. Here if you see, PC int is actually pin change interrupt. That is, almost every pin has an additional feature called pin change interrupt, and therefore you could use these to take care of handling asynchronous events. If there are several asynchronous events, you could use such a microcontroller and such a feature on these microcontrollers. Now, you need a clock to operate a microcontroller, and the reason is that a microcontroller, as an example of a logic circuit, is of the type what we call as synchronous, and it has a sequential synchronous. So, for that you need a clock signal. So, you have to derive that clock signal in some way. One of the methods is that you would use an internal source of clock, internal oscillator, and you connect an external component to determine the frequency of that clock. That would increase the cost, because that external component would take up 2 pins, maybe 3 pins, maybe 1 pin, and it would be an additional cost. If you want to keep the cost down, you would like the microcontroller to be able to generate a clock signal internally, and such a feature is called internal and external clock sources. And usually a very convenient way of generating internal clock signal is by way of an RC oscillator. You can create a RC oscillator. I can show you a simple example of a RC circuit to generate clock. Here is my NOT gate, and I would take a NOT gate of the type of Schmidt inverter. This is a Schmidt inverter. This has input and this is the output. I connect a capacitor here and I connect a resistor here, and we can consider, let us say the input is 0, because this is an inverter, the output becomes 1. It charges the capacitor through this resistor using the time constant R and this capacitor C. As the capacitor gets charged and the voltage on it increases, goes beyond the VIH threshold, it turns the output low, and now the capacitor discharges through this, and so it leads to an oscillation. If you see the waveform here, between two thresholds you would see the waveform on the capacitor going like this, and the output would be a rectangular waveform, and the frequency will be determined by the R and C. And you see, you can integrate all these features on the substrate of a microcontroller. The only problem is that the value of R and C are affected by temperature and voltage variations, and so the clock frequency may not be very accurate. And so in such applications where not a very accurate clock is good enough, you could use the feature of an internal RC oscillator, because it would keep the cost down. In case you want higher precision, then you could use the same internal oscillator, but with external frequency determining components such as a quartz crystal to give you higher accuracy clocks. Now another interesting feature that these microcontrollers offer is what is called as clock scalability, and in fact MSP 430 offers this feature. What is the meaning of clock scalability? Meaning that you can change the system clock, the internal clock or external clock signal that we were just talking about. You could change the frequency of that clock at runtime. Normally you would fix the frequency and you may not want to change it. But today, because our modern microcontrollers are CMOS based, the power dissipation of a CMOS circuit is directly proportional to the frequency of operation. And in case the microcontroller application deems it necessary that there is no available job to do, why to waste power by continuing to clock at a higher frequency? During that time, it can reduce the power dissipation by scaling down the clock. And when some activity is expected or some activity becomes available, it can increase the clock frequency to a higher value, so as to be able to perform the perform the tasks in a timely fashion. So it should have the ability to change the clock frequency at runtime depending upon programmed logic. Having this feature will make a more battery efficient system. And so you, as a designer, when you are looking for various features, you should read the data sheet of that microcontroller to find out whether clock scalability is an option or not. Also, modern microcontrollers operate at great high frequencies, in which case the power dissipation may increase, and to control that, oftentimes the chip is partitioned in multiple voltage domains, and therefore you would find that your microcontroller requires 2 or 3 different supply voltages. We will come to that feature when we talk about the ecosystem of a microcontroller. MSP 430 is the ones we are going to use, is a simple microcontroller, and it requires just one voltage supply, but many ARM and advanced microcontrollers may require 2 or even 3 supply voltages, and it becomes the responsibility of you, the designer, to provide those voltages. Modern microcontrollers operate at very low currents, and typically these currents range in this these currents are in this range, roughly 1 milliampere per megahertz to roughly 0.1 milliampere per megahertz. So which means if your microcontroller offers 0.1 milliampere per megahertz kind of a feature, and if you are going to clock it at 50 megahertz, then you can expect that the total supply current, what we will call as ICC, will be about 5 milliampere. This you will have to provide, that the power supply should be capable of providing 5 milliampere specifically to the microcontroller, and this is a very low current. This is a great advancement that has happened. Also, to continue to optimize the available source of energy, battery, modern microcontrollers operate in multiple modes of operation, and they are invoked to ensure that battery is used optimally, and these modes are called active mode, a sleep mode and power down mode. Inactive mode is the normal mode, is the mode you would like the microcontroller to operate at when you want it to give the best performance. But in case the microcontroller system can find out that it is not being used, it could switch to the sleep mode of operation, where the clock signal is cut off to certain functional units inside the microcontroller, and when the clock is removed from a microcontroller function block, it reduces the power consumption. So, you invoke sleep function so that power dissipation is reduced, and in case there is no activity happening, you can even go to what is called as the power down modes of operation. We will see this in the context of the microcontroller features when we discuss them. They operate, modern microcontroller operate at using a wide power supply voltage ranges, some between the range of 0.9 volts to 6 volts. They offer, or they have several sources of interrupts. They are called power on reset, user reset, brownout detector reset and watchdog reset, and we will again consider this in detail when we look at the ecosystem of a microcontroller in detail. Watchdog timer is, if it is available, would be available with an independent clock, and the reason is when you consider it with this feature that your microcontroller can operate in various modes of operation. In case the microcontroller goes in power down mode, it would cut off the clock for the watchdog timer, making it ineffective, and therefore you do not want that to happen. So, usually watchdog timers come with an independent clock that will not be shut down in case you choose the power down mode. Also, the brownout detector reset has a programmable threshold. Brownout detector means whenever there is a low going voltage spike on the power supply, this low going voltage spike may potentially corrupt important registers inside the microcontroller, and one way to ensure that the corrupted values do not doom the system, it does not block the system. One way to counter that is to reset the system completely, and you can set the threshold of voltage at which this feature, this reset will kick in. That is the meaning of programmable threshold on BOD reset sources. Then our modern microcontrollers are great examples of what we call as mixed signal circuits. Mixed signal means it is not purely digital, it is not purely analog, but it is primarily a digital circuit with analog capabilities, and therefore it is classified as a mixed signal circuit. And for the mixed signal capability, one important feature is that it should have an integrated analog to digital converter. Analog to digital converters are of various types, and what we have is successive approximation type of ADC, a dual slope type of ADC, a delta sigma type of ADC, and the resolution of these ADCs range between 8 to 16 bits, and therefore when you are selecting a microcontroller specifically from the point of view of analog performance, you should read the details in the data sheet to find out what kind of ADC it offers, what is the resolution of this ADC, and also the speed of this ADC, because speed is heavily dependent on the architecture of the ADC, meaning is it successive approximation or a dual slope or a delta sigma. Dual slope ADCs are not that fast. If you want high speed of conversion, higher rate of conversion, then you may have to choose SAR, successive approximation type of ADC, or delta sigma type of ADC, and this information is available in the data sheet. We will consider this in detail when we are looking at the way a microcontroller samples external signals. In that context, we will look at this feature again. Therefore, resolution and speed of ADC is an important consideration, important feature to for you to verify before you select an appropriate microcontroller for your application. As part of the mixed signal capability, a microcontroller may offer hardware DAC, meaning it has an integrated digital to analog converter. You simply load a number into it and the DAC will convert it into a corresponding proportional analog voltage. Or if it does not have a dedicated DAC, it would offer you that feature through what is called as pulse width modulation. We will go in detail of how to get DC voltages or analog voltages out of a pulse width modulated digital signal. As part of the mixed signal requirement, you would see that such microcontrollers have multiple power supply pins dedicated to supply power to the digital part of the circuit and some pins dedicated to supply the voltage to the analog part of the pins. This is so that the digital power supply pins, often the voltage there gets corrupted because of the switching action inside a logic circuit, and this may leak into the analog circuit. So, best way is to have independent power supply pins. So, you have to be careful when you have multiple independent power supply pins to ensure that those power supplies are fed correctly and that the noise on logic, the supply voltage for logic circuit does not leak into the power supply pins of analog circuits on those microcontrollers. Here we can see, go back and look at the pins of this AVR microcontroller, and you notice that it has a VCC and a VCC. This VCC means it is for the logic part of the circuit inside the microcontroller, and AVCC means it is for the analog VCC, specifically the ADC and the voltage reference source. And it also has two grounds, although it does not explicitly mention. This ground is paired with this VCC here, digital VCC, and this ground is paired with the analog VCC. It turns out that on our MSP 430 there is no separate power supply pins for analog and digital part of the circuits, even though MSP 430 is also a mixed signal type of circuit. It has ADCs, but they have not deemed it necessary to separate the power supply pins. So, this is an important point to keep in mind when you are designing a circuit, a system using a microcontroller, whether it has individual pins or independent pins. I mean, does it have a common pin or does it have independent pins for power supply, for VCC for the analog part of the circuit and the digital part of the circuit. Then for measuring time and other events, modern microcontrollers would offer you a timer as well as a counter, and the resolution of these timers and counters range between 8 and 16 bits, which means it can count 2 raised to power 8, which is about 256 events, or it can count 2 raised to power 16 events, which is about 65,000 or so. And if you can have a clock signal for such 8 or 16 bit counters, it would be able to measure that much time. That is, let me explain. If I have a timer with 16 bits, that means it can count 2 raised to power 16 clock pulses, which is equal to 65536 clock pulses. And if the clock period is TCLK, if it is say 1 microsecond, then the total time that the timer will be able to measure for you is 65.536 milliseconds. If you want to measure more time, one way would be to increase this period, which means reduce the frequency, and if you divide it by 10, you would get 10 microsecond, and then you can measure up to 655 milliseconds and so on. So, you can trade off the resolution with the dynamic range, that is the maximum time that you can measure, and that choice would be available to you. What do you want to have? It also offers high frequency pulse width modulation signals with various options. One of them is called dead zone. Dead zone allows you some rest time between two signals, so that some specialized devices require it. You should read the data sheet of your microcontroller to find out what are these options available to you. Modern microcontrollers may need to communicate with the outside world through in your application, and so they offer general purpose communication protocols such as UART, SPI, serial parallel interface, serial peripheral interface, I2C, which is inter-IC communication, and something called a one-wire protocol. It may also offer, some of them may also offer specialized communication protocols such as CAN, control area network, LIN, Ethernet, USB, and if it is USB, you have to find out whether what type of USB option is available. Some of them are called device USBs. There are other varieties called OTG, like you have on your phone, mobile phone, smartphone, and on your desktop computer, the USB type is what is called as host USB. So you must find out what is your application. When you want USB functionality, you want to know what do you want to connect through this USB, so that you can select appropriate type of USB function. Then it may offer you Wi-Fi, built-in Wi-Fi. It may offer you regular Bluetooth or low energy Bluetooth and other RF communication protocols. Some microcontrollers may even offer specialized functions such as a floating point unit. A floating point ALU will perform floating point operations quite quickly. They may also offer encryption units to encrypt the data before you save them, and these are called hardware accelerators. There may be hardware accelerators for other activities. Most modern microcontrollers will offer in-system programming, and some of them may also offer in-application programming. Our MSP430 that we are going to use offers both these modes, and in fact our kit operates through the in-application programming mode. We will be able to upload program while the system is still on, and so this is one of the modes of programming the microcontrollers. Modern microcontrollers also offer on-chip debug capability, which means while you have built your system, if your system is not working properly, you can invoke the on-chip debug function to find out what is wrong by inspecting the internal registers and memory locations. Modern microcontrollers may offer JTAG, which is a Joint Test Action Group protocol, which allows you to invoke the on-chip debug function. And many high-end microcontrollers may be using the DMA capability to speed up the communication between memory, speed up the rate of transfer of data between memory and ports. For developing applications, you need tools, and these are the application development tools. You need a development platform. Usually these days, PC, whether a desktop or a laptop, is used for application development. It must be able to run an assembler and a compiler. You should have simulator and debugger. You should also have a evaluation board so that you can test your small programs, and you should have a mechanism to download code from this platform into the memory of your target microcontroller. And oftentimes you may be required to emulate or debug your code, so you should have a on-chip debugger facility to access the on-chip debugger through the JTAG interface. Apart from the application development tools, you may also be required some system development tools, and for that, once you have finalized your requirements, you may want to create a circuit board. So you need some circuit prototyping facility. You may also need schematic capture and PCB layout tools. I mentioned that in the first lecture that it would be nice if you could download and use EagleCAD, which is a PCB layout software. You should have circuit soldering facility, maybe a solder iron for small jobs, and increasingly as the sizes of components are reducing, you may want a pick and place machine as well as a soldering oven for automatic soldering of these components. You may need a microscope or a magnifier to magnify and inspect your fabricated circuit board to ensure that there are no shorts or no tracks are open. For electrical observations, you may need an oscilloscope, a logic analyzer, which is nothing but like an oscilloscope, except you are able to look at multiple channels as a function of time. So, an oscilloscope does this. An oscilloscope allows you to look at time versus voltage plot of any waveform. This is your oscilloscope. On the other hand, a logic analyzer allows you inspection as a function of time, but of logic levels. So, you can look at a signal and it will show you on this waveform, like this is the way it. And unlike oscilloscope, which usually is 1, 2 or 4 channels, logic analyzer, this is oscilloscope and this is logic analyzer, will give you 8 or 16 or 32 or 64 simultaneous signal observation capability. So, a logic analyzer is a very useful device to have, but increasingly, because my microcontroller system is a mixed signal system, I need a new instrument called mixed signal oscilloscope. A mixed signal oscilloscope is an oscilloscope which is a combination of normal oscilloscope and normal logic analyzer function integrated in a single instrument. It is called mixed signal oscilloscope. Apart from that, you would need a digital multimeter. LCR bridge is a good tool to have, good instrument to have in your lab, and a variable bench power supply, so that you can use that to power your system while testing. These are the system development tools. Now we come to the end of this lecture. In the next lecture, we will discuss various elements of microcontroller ecosystem, how to make sense of these elements and how to use them in our application with the ultimate goal of creating a successful embedded system design. Thank you very much. I will see you soon.